Chapter 19 is dealing with magnetism, and I always wondered why when I first started this course, I wondered why we were dealing with magnetism the same semester we were dealing with electricity. So this chapter is going to establish the relationship between moving charges and magnetic fields. So we've probably dealt with magnets at some capacity. We've got refrigerator magnets. Maybe in school you had a science teacher that had magnets in his classroom or something like that, and you noticed that they were attractive and repulsive. And if you ever saw, if you've ever seen a bar magnet that's not marked, you don't really know, how to situate them to where they're repulsive or attractive. So a lot of magnets will mark them with their poles. So we mark them north and south, kind of like with electricity, where we have negatively charged particles and positively charged particles. The notation is just conventional, and we'll actually see where we'll talk about the Earth and its magnetic field, how it can kind of be confusing at times. But so if you've ever tried to push two magnets together, either they really attract each other or they'll repel each other, depending on which sides of the magnet, the two magnets you get close to each other. So if you have magnets that are marked, you'll see that their north poles and their south poles, if they come close to one another, they'll repel each other, right? So kind of like charges repel and opposite charges attract. It's kind of a similar principle, right? Two of the same poles of two magnets, if you bring them close together, you'll feel a repulsive force. If you take opposite poles of two magnets and you bring them close together, they'll attract each other and then they'll stick together, and it'll be difficult to pull them apart. So again, similar to the principles of attractive and repulsive charges in electricity. If you took one of those magnets, one of those bar magnets, and somehow you were able to cut it in half, you actually don't cut it into its north and south pole. What you actually do is you generate another pair of magnets. So if you keep doing that over and over again, you'll continue to create multiple bar magnets. So we'll never have an isolated, or at least up to this point, we've never discovered an isolated magnetic pole. Right? So there's never been a north pole that has been discovered without a corresponding south pole. So you can't have a magnetic monopole, at least as far as we know. So this is a diagram of our planet, and so we have, if you ever did any land navigation, or if you ever did any hiking or anything, you messed around with a compass before, maybe you've seen that your magnet doesn't point directly to the north pole of the Earth. It's actually pointing to magnetic north, right? Sometimes you may have heard that, geographic north and magnetic north. So if you look at the needle of a compass, this part it's labeled red, it says north, it will align with the Earth's magnetic field, right? So your compass is actually pointing towards the magnetic pole of the Earth. So the Earth is basically a large magnet. It's proposed, the theory is that it's due to the current generated by the molten material that's actually flowing deep inside the Earth. And we'll talk about how a current generates a magnetic field later. But that's the theory behind why the Earth behaves like a magnet. And our magnetic North Pole is actually it actually behaves like the South Pole of a magnet. So what we have is the needle of the compass is magnetic, and so it's actually aligning with the South Pole. So this north end of your compass needle is actually being attracted to the South magnetic pole. So our geographic North Pole corresponds with the magnetic South Pole of the Earth. So magnetism behaves similarly to electricity in that it's a long-range force, but it doesn't attract charged particles, right? So it's not necessarily the same as electricity, but we'll see that it's similar to it in that it generates a field, right? So we can't have a single isolated pole of a magnet, whereas we can have a single isolated positive or negative charge. We can't do that with magnets. So we can use a compass not only to find out the direction of the north and south pole of the planet, but we can use a compass needle to detect the direction of any magnetic field. So if I had a compass and I brought it close to a magnet, the needle would actually align with the magnetic field of that magnet, because it's much stronger the closer you are to it. So another similarity to electricity is that it behaves like a field. It's a long-range force, but we can't have a single magnetic pole. So we've got naturally occurring magnetic materials, some rare earth metals. That's what we use to make like our refrigerator magnets, you know, or bar magnets that you see in a lab or something like that. So those are permanent magnets. We also have ferromagnetic materials like iron and cobalt and nickel. So those are materials that are attracted to permanent magnets, and that we can magnetize. We can make magnets for a certain amount of time. They're not permanent magnets, but we can make them magnetic. And then there is a third way we can generate a magnetic field, and we'll talk about that later when we talk about how current generates a magnetic field. So if you had 120 here, if you talked about it, we talked about torque, and we talked about the right hand rule. So what I did was I put the my lectures from 120 dealing with torque. So I'm just going to refer to the first slide of that, because we're going to have to deal with the right hand rule again. So if you maybe skip that, depending on where you took your first semester of physics, I'll do like a recap on the right hand rule. But we have to deal with 3 dimensions when dealing with magnetism. So our notation, because I'm not very good at drawing a 3D Cartesian space, right, an XYZ plane. So we deal with 3D, but we deal with it in like on a 2D plane. So we've got vectors in the X direction, vectors in the Y direction. Those are arrows we can draw on our paper. But if we have a vector that's going into the page, right, if you're sitting in front of your device right now, your laptop, whatever, if you point your finger towards the screen, that's a vector that's going into the page. That's a vector going into the page. And we're going to use X's to denote those as vectors going into the page. So think about it like an arrow, right? If you've ever seen an arrow, it's got like a veins on the back, like feathers. They use plastic a lot now. But if you have 3 or 4 veins, if you're looking at the arrow from behind, you'll see the veins. They'll either make an X or maybe they'll make a Y or something like that, depending on how many veins you have. So think about this as like an arrow going into the page, and you see the back of the arrow. We're going to be dealing with currents that are going into and out of the page too. So we try to use the same notation or the same figure, but we put a circle around it just to kind of represent that it's like a current inside of a wire. And then vectors going out of the page, if you think of the tip of the arrow coming towards you, that's a vector out of the page. So the dots represent the tip of the arrow's coming out of the page, and then the X's represent the back of the arrow going into the page. And so we'll do the same thing with current. We'll have a dot, and then we'll put a circle around it to represent a current that's coming out towards us. So our convention is towards us is going to be the positive Z direction. Okay, so I stole this because I can't draw this very well. So if we have a 2D plane, we've got X, we've got the Y direction. This vector right here, you can kind of tell it looks like it's coming towards you. That's the positive Z vector. Right, so that's the positive Z direction coming out towards you. If you had another vector going into the page, that's going to be the negative Z direction. So we have to, I'll do a quick recap on the cross product. And what I'll do, since I don't really have the technology to make a video showing you this and walking you through it, I'm going to upload some other videos that help explain this right-hand rule if you haven't seen this before, or maybe it's been a while since you've taken 120. So the cross product of two vectors is actually a vector. So we talked about the dot product when we dealt with work and a couple other topics. So dealing with work was the dot product between two vectors, right? And we got a scalar back, right? Work is energy; it's a scalar property. The cross product between two vectors is a vector. So if I have vector A and vector B, the cross product between those vectors is a vector, and that's going to be perpendicular to the plane where vectors A and B lie. So if this was like the XY plane, you'd have the cross product of these two vectors that are lying on the XY plane would be in the Z direction. Right? So it's perpendicular to both of these vectors. It's always going to be perpendicular. Its magnitude depends on the angle between the vectors. So the cross product is AB, the magnitude of A times the magnitude of B, times the sine of alpha, in this case, the angle between the two vectors. So we see sine of 0 is 0. So if A and B were in the same direction, their cross product would be 0. So we wouldn't have a vector perpendicular to them. So we go from 0 and then we go to 1. So sine of 0 is 0, sine of 90 is 1. Right? So if these two vectors were perpendicular, right, if A and B were perpendicular on this plane, this vector would be at a maximum. Right? So you think sine of 0 is 0. As you increase that angle between the two vectors, that sine term gets bigger and bigger and bigger until you get to 90 degrees, and then it gets to 1. So the direction is always going to be the same, but the magnitude is dependent upon the angle between them. So if we want a maximum cross product resultant vector, alpha is going to be 90. If we want no cross product vector, alpha is going to be 0. And so I put this down here to kind of give us multiple occurrences of the cross product and kind of show you the right hand rule again. So I started with this cross product. X cross Y is equal to Z. So how am I going to determine the direction of the cross product X cross Y? So we're going to use the right hand rule. We're going to take our right hand and we're pointing our fingers in the direction of the first vector in the product, X. Okay. So my right hand, my palm is actually facing up. So I have to use my right hand. My palm is facing up. My fingers of my right hand are pointing in the positive x direction. And what I want to do is I want to curl my fingers in the direction of the second vector. So my palm is still facing up. My fingers are now curling kind of counterclockwise. My fingers are now pointing in the positive y direction. What direction is my thumb pointing in? It's pointing towards me. It's pointing in the positive z direction. So that's my right hand rule. That's how I determine quickly the direction of the resultant vector. So right hand, fingers in the direction of the first vector x. My palm is facing up. Curl my fingers in the direction of y. Now my fingers are pointing in the positive y direction. My thumb is going to be pointing in the direction of the resultant vector. So try that here. Try that here. The vectors don't have to be perpendicular for us to use the right hand rule. So point your fingers in the direction of A. You curl them in the direction of B. Your thumb is going to be pointing up in this direction. And so try that right hand rule with these vectors. Okay, do y cross z, do z cross x, and then flip the order of the vectors. So when you did x cross y, now do y cross x, z cross y, and x cross z. You'll see that the vector product is not commutative. So x cross y is not the same as y cross z. What you'll see is when you excuse me, when you change the direction, or you change the order of the vectors, the direction of the resultant vector is opposite, right? So it's actually, if I do y cross x, my thumb is going to be pointing in the negative z direction. So practice with these. You know, you want to pause the video if you want. Try these out. Okay, try all 6 of these and see if your thumb is pointing in the direction of these vectors with each cross product. And so the reason we recap the cross product is because if I have a uniform magnetic field, all right, so we've got a magnet and it's generating a constant magnetic field in some direction. We call that magnetic field B. We use B to use that or to denote the magnetic field. So it's a vector, and if we have a charge, in that magnetic field, the first thing we notice is that if the charge is not moving, there's no net force. If the charge is not moving, the magnetic field does nothing to that charge. Okay, but once the charge starts moving, so say we give this charge a velocity v, right? We've got some device that fires charge off into a magnetic field, right? So this charge is moving in this direction with a speed v. We see that if the positive charge is moving in the same direction as the magnetic field, there's still no net force. So a stationary charge doesn't experience a force, and a charge moving in the same direction as the magnetic field also does not move or does not experience a force. But once we take that particle, and if it has a velocity that's not parallel to that magnetic field, we see that it experiences a force. It changes its path, right? So it doesn't stay along that same path, so it's got to be experiencing a force. It's got to be accelerating. And we see that the force on that moving charge is the cross product between the particle's velocity vector and the magnetic field. So if you notice, this is similar to my vectors A cross B in that first slide of the rotational dynamics presentation. So this is A, this is B, and then the cross product A cross B was perpendicular. So what's actually going to happen is if we take this this particle launcher, whatever this device is, and we fire a particle in this direction, as soon as it enters this magnetic field, it's going to experience a force in that direction. Right? And so this force vector is perpendicular to both the velocity vector and the magnetic field vector. So our formula for the magnetic force on a moving charge, it's the cross product of the velocity vector with the magnetic field vector. So order matters here, right? Just like I talked about earlier, where it's not commutative, right? It's a cross product between the velocity vector and the magnetic field vector. So it's V cross B, and it's also directly proportional to the charge of that particle. Now notice I don't have absolute value bars here, so we're going to have to talk about how the sign of the charge, whether it's positive or negative, how that affects the direction of the force. Okay, so this isn't necessarily the magnitude of the charge, but it is directly proportional to the charge. So we use our right hand rule just like we did with our two vectors. You point the fingers of your right hand in the direction of the velocity vector. You curl your fingers in the direction of B. Whatever direction your thumb is pointing is the force on that particle. Now this is for a positively charged particle, and you might be able to guess that if we had a negatively charged particle, what we were going to have to do. So we go through the right hand rule, and if this is negative, we'll have a negative sign here. Right? We'll have a negative sign here. This never generates a negative sign because V and B are the magnitudes. Right? V and B are the magnitudes. You'll get negative signs if the sine function gives you a negative sign back, but we're just going to rely on the right hand rule to give us the direction on the force. So if this is negative, then we're going to have to switch the direction. So whatever direction my thumb is pointing in for a positive charge, I'm going to have to flip that direction for a negative charge. And I'll do a couple examples here. So magnetic field is measured in Teslas. So that's the SI unit. We also use Gauss, but for our purposes, Tesla is most convenient. So you see that this is coulombs, this is meters per second. So the coulombs per second are actually amps, right? So the units of these two terms are actually amp seconds, or excuse me, amp meters, right? So these are amp meters. If I divide both sides by amp meters, so I get Newton per amp meter. So 1 Tesla is a Newton per amp meter. Alright, so here are a couple just diagrams. I've actually got 2 slides so we can do some right hand rule practice. So the top left corner, I'm going to do the right hand rule here, if you can go along with me. So we're going to use our right hand, point our fingers in the direction of the velocity vector. So my palm should be like facing the screen of my computer right now. And it says to curl your fingers in the direction of the magnetic field, but I see that the magnetic field is in the same direction as the velocity vector. So I can't curl it. If I don't curl my fingers, then the angle between the velocity vector and the magnetic field vector is 0. So that means the force on that charge is 0. So the force on this charge in the top left corner is 0. We go to the top right. I'm going to take my right hand, point my fingers in the direction of the velocity vector first. So now my palm is still facing the computer screen, but my fingers are pointing up in the positive Y direction. So in order to curl my fingers in the direction of B, I actually have to rotate my hand. So now my palm is facing the right. So I rotated my hand, my palm is facing the right. My fingers still have to stay in the direction of the velocity vector. So my fingers are still pointing in the positive Y direction. My palm is facing, or is pointing in the positive X direction. So I can curl my fingers in the direction of B. So I'm curling my fingers in the direction of B, My fingers are now pointing in the positive x direction. My thumb is pointing where? Which way is my thumb pointing? My thumb is pointing, hopefully your thumb is pointing in the same direction right now, into the page. So my thumb is pointing towards the computer. So that means the force on the charge in the top right is in the negative z direction. It's into the page. Bottom left, let's do it again. Fingers in the direction of the velocity vector, so my fingers are in the positive x direction now, and I want to curl them in the direction of the magnetic field. What's the direction of the magnetic field here? I see x's, that's the back of my arrow, so the magnetic field vector is into the page, so it's in the negative z direction. So my fingers are pointing in the negative x direction, my palm is facing the laptop right now. So I can curl my fingers into the computer screen. What direction is my thumb pointing in? It's pointing in the positive y direction. It's pointing up right now. So the force on this particle is the positive y direction. So this diagram looks very, very similar. Velocity vector is the same. Point my fingers in the direction of the velocity vector, positive x. Curl my fingers in the direction of the B field, negative z, into the page. My thumb is still pointing up in the positive y direction. But I notice that this is a negatively charged particle. So if I go back to QVB, the charge is negative, so the direction of the force is switched around. So the direction of the force experienced by this particle is actually in the negative y direction. So I go through the right hand rule the same. V in the positive x, curl my fingers into the page. My thumb is pointing up, but at this stage I remind myself I'm dealing with a negative particle, so I just rotate my hand, point my thumb in the opposite direction, negative y. Let's do a couple more examples. I'm going to go through each one of these, and I'm going to do each one for a proton and then do it for an electron. So I'm going to do each one for a proton and an electron because that's, to me, that's easier. I go through the right hand rule, identify the direction of the force of the proton, and then I just switch it to get an electron. Alright, so hopefully you're doing this along with me here. Let's do part A. Right hand, fingers in the direction of V, that's up, positive y direction. The magnetic field is into the page, got the back of the arrow, so I curl my fingers into the page. My thumb is pointing to the left, the negative x direction. That's for a proton. So the force on this particle is the negative x direction for a proton. Now I want it for an electron. All I've got to do is flip my hand in the opposite direction, and now my thumb is pointing in the positive x direction. So the force on an electron would be the positive x direction, the force on a proton would be the negative x direction. Part B, fingers in the same direction as before, velocity vector still in the positive y direction, but now I've got to curl my fingers in the positive x direction. So my fingers are pointing up, positive y. I have to turn my hand, I have to rotate my hand so my palm is facing the positive x direction, curl my fingers in the direction of B, positive x direction. My thumb is pointing into the page. My thumb is pointing into the page for part B. So for a proton, the force is into the page. For an electron, the force is out of the page. So flip your hand around at the end for an electron. Your thumb is pointing towards you. Part C, my velocity vector is in the negative x direction. So I point my fingers in the direction of the velocity vector, negative x, but my palm is now facing down. And my palm is facing down because I'm going to have to curl my fingers in the direction of the magnetic field. So velocity in the negative x, curl my fingers down in the direction of B. My thumb is pointing at me right now. My thumb is pointing out of the page. So the force on a proton in part C is out of the page. Force of an electron, flip your thumb, it's into the page. Part D, velocity vector, same direction. So my velocity vector is in the negative x direction, but I have to curl my fingers out towards me. So my palm has to face me. See, these are the tips of my arrows coming out towards me. So velocity in the negative x, my palm is facing me right now, so I have to curl my fingers towards me, the direction of the B field. My thumb is pointing in the positive y. I'm giving my computer a thumbs up right now. Alright, so that's the force on a positively charged particle. For the negatively charged particle, I flip it, I'm giving it a thumbs down. Okay, the force is in the negative y direction. So parts E and F, the vectors are not perpendicular to one another, but we can still use the right hand rule. So I point my finger in the direction of V. Okay, so it kind of looks like I'm doing a little teapot thing right here with my right hand. Okay, so my velocity vector is kind of pointing in the positive x, positive y direction, but I can still curl my fingers down towards the direction of B. Okay, so think of it as like you're closing this angle up with your hand, right? So your hand's going along the velocity vector, and you just want to curl your fingers down, okay, like you're closing that angle up. So my fingers going this way, curl them down this way. And so now if I do that, my thumb is pointing into the page. My thumb is pointing into the page. That's the force for a positive particle. Flip your hand around, the force on an electron or a negatively charged particle is out of the page. Same thing here. We've got my velocity vector here, so I'm going to point my fingers in this direction, but I still want to close them up in the direction of B. Okay, V cross B. Alright, so point your fingers in the direction of B. My palm's kind of facing down towards the ground a little bit, so I'm going to curl it. I'm going to curl my fingers under and around like that in the direction of B. My thumb's pointing towards me. So the force on a proton is towards me in part F, and the force on an electron is into the page for part F, because I have to flip my hand at the end. So for all of these, so this was slide 10, this is slide 11. If you go here, first page are all those examples that I just did. Okay, first page is all those examples. These are the right hand rules for slide 10. These are the right hand rules for slide 11. So I just kind of recreated the diagrams a little bit, but what I did with the vectors was I took the tail of the velocity vector connected to the tail of the magnetic field vector. Right. So in these 2D examples, it might be a little bit easier to see what direction you're curling your fingers. Okay. And I have another video that kind of explains the right hand rule, so I'll upload that just for a little bit extra, because you can't really see what my hand is doing, so I'll put some extra stuff up there for help. And if anything throws you off, just get in touch with me. We can zoom and maybe you can see what I'm doing there with my hands. So it's a three-dimensional process. Okay, we got to deal with the cross product. So it deals with the speed of the particle, the strength of the magnetic field, and the charge of that particle. So we've got an electromagnet. We'll talk about how we create electromagnets later. So we're generating a magnetic field of 1.5 Tesla. We're going to be dealing with Tesla throughout this course. So 1.5 Tesla, usually that's kind of what you see, 1-2 Tesla, something like that. We've got a proton moving through the field with a speed of 6 times 10 to the 6 meters per second. Very fast, but we've seen, like we saw in chapter 16, that a charge free to move in space under an electric field can move very quickly. So we've got a speed of 6 times 10 to the 6 meters per second. It's asking for the magnitude of the maximum magnetic force that can be experienced by the proton. So I'm not given directions or anything right here, but we want the maximum magnetic force and the maximum acceleration. So we know that in order to produce the maximum force on a particle, that particle has to be moving perpendicular to the magnetic field. So that means the angle between them is going to be 90, and the sine of 90 is 1, and all I have to do is calculate QVB. So for the maximum magnetic force, the V vector and B vector are perpendicular to one another. Sine of 90 is 1, so we just have to deal with QVB. So it says it's a proton. It's positively charged, 1.6 times 10 to the negative 19 coulombs. I'm given the velocity and the magnetic field. All I have to do is calculate QVB, and that's the maximum magnetic force. I could call that piconewtons, right? If you remember from last chapter, 1.44 times 10 to the negative 12 newtons. They're asking for the maximum acceleration. I'm just going to use Newton's law, or Newton's second law. Take the max force divided by the mass of the particle, which they said is a proton. Mass of a proton is 1.67 times 10 to the negative 27 kilograms. So the max acceleration is the max force divided by the mass, and I get 8.6 times 10 to the 14 meters per second squared. Don't let the large numbers scare you. Okay, we're going to get large accelerations. Speeds are going to be large. Okay, so it's a very large, very small force on the particle, but the mass is also very, very small. So we're dealing with very large accelerations. So you may have seen a mass spectrometer before. Maybe at this point in your career, maybe if you're a biochem student, you might have dealt with a mass spectrometer before. So we're gonna talk about what that does in very, very basic terms. I drew a little diagram here. Okay, so we're gonna go back to one of our right-hand rule examples. Okay, so let's say we've got a velocity vector that's going in the positive x direction, and then there's a magnetic field going into the page. If I do the right-hand rule on this, I go V, my fingers are in the positive x direction, I curl them into the page, my thumb is pointing in the positive y direction. So as soon as this moving particle enters this magnetic field, it feels a force in this direction. So what happens to this velocity vector? It changes direction, right? Changes direction. Now it's got a velocity in the x direction that's not changed by this force vector, but it's accelerating in the y direction, right? So it's going to change its direction, but every time it changes its direction, this magnetic field is uniform, so it's always going to generate a force that is perpendicular to it, right? So this velocity vector is here. I do the right-hand rule again. It's experiencing a force in this direction. So the direction of the force isn't constant. So this velocity vector is going to change its direction again. It's going to accelerate a little bit more in the y direction. And then as the velocity vector changes direction again, the force vector changes direction again. And it keeps doing that, right? So you see this velocity vector keeps changing direction, and even when it hits the y direction, let's say the velocity vector was completely in the y direction, if we do the right-hand rule here, V cross B gives me a force in the negative x direction. And so it's going to keep turning, right? So this velocity vector keeps changing direction, because when this particle is in a uniform magnetic field, it actually exhibits circular motion. So it's going to follow a circular path because this force vector keeps changing. So I can describe the force on this charged particle as a centripetal force, right? Because it's actually accelerating in the centripetal direction. But in 120, we said the centripetal force is not its own special force, right? There's not this unique force that we call centripetal force. It's due to some agent that we already know of, right? So when we were doing centripetal acceleration, it was due to a tension, or if it was due to a normal force when we were doing like the banked curves, or if it was due to friction or something like that. The centripetal acceleration in this example is due to the magnetic force. It's the magnetic field that's causing this particle to follow a circular path. So if I can set QVB, notice that the velocity vector and the magnetic field vector were always perpendicular in this case. So if QVB, if I set that equal to mv squared over r, a velocity term cancels out. I get QB equals mv over r. So what I did was I solved this for both r and v. So I've got these two expressions for the radius of the particle's circular path and then the velocity of that particle, the magnitude of the velocity of that particle. So these are going to come in handy. I can also talk about it in terms of angular velocity. Sometimes we refer to it as angular frequency. So omega is v over r from our circular motion from 120. So v over r is actually qb over m. If I solve this for v over r, divide both sides by r, I get qb over m. So the angular velocity is dependent upon the charge of the particle, the mass of the particle, and the magnetic field strength. So you'll see this, maybe, I'm not sure if it's in this edition of your textbook, but there is a table of charge to mass ratios of isotopes. And that's how we use a spectrometer to identify something, by their charge to mass ratio. And sometimes, maybe in a WebAssign problem, they'll ask you for the cyclotron frequency. So this is the angular velocity. Sometimes we refer to it as angular frequency. The frequency is the angular frequency over 2 pi. So the cyclotron frequency is QB over 2 pi m. So these are some expressions that are going to come in handy with our examples and WebAssign. So we've got the cyclotron radius, or the radius of the orbit is mv over qb, and we've got this expression for the cyclotron frequency. So we've got a basic diagram of a mass spectrometer. Okay, a mass spectrometer. And we'll talk about this velocity selector thing in a second. So there's an electric field here. Okay, so this red plate here is positively charged. The blue plate is negatively charged. So there's an electric field away from the positively charged plate towards the negatively charged plate. And that electric field strength is 950 volts per meter. Also Newton per Coulomb. Okay, so 950 volts per meter is the strength of the electric field. And throughout this whole system, there's a magnetic field that's going into the page, and that is 0.93 Tesla. So the magnetic field is into the page, and it has a strength of 0.93 Tesla. We're looking for the radius of this path. We're looking for the radius of this circular path. So this charged particle, it travels through this velocity selector. We'll talk about why we call it a velocity selector in a second. Travels through this velocity selector. It's got a constant velocity in the positive x direction, and then it hits this uniform magnetic field, and then it experiences that magnetic force that causes it to travel in a circular path. So we're looking for the radius of this path. Okay, we're looking for the radius of this path. It's a singly charged ion with a mass of 2.18 times 10 to the negative 26 kilograms. Okay. So what I'm going to do is I'm going to pick up this solution because I've got a timer on my phone. I think when I hit the 45-50 minute mark I start having audio issues. So I'm going to come back, start this problem, start this example at the beginning of the next video. Alright, see ya.